unchanged. And this also is these rotations, they form a group. And again, there the symmetry is coming. So now, symmetry we will just broadly define as a characteristic which is same or which is unchanged in any rotation or reflection. Now let us introduce symmetry. Now what is symmetry? Let us say a given object. We define symmetry. So in a physics term, like a given object said to display symmetry, if it is found to be invariant. We may now may not use the word invariant directly because we are learning quantum mechanics. The invariant term can be used later. Maybe we can say unchanged under a certain operation or a transformation. So again, some physical observables do not change with time and are called constants of motion. Now, constants of motion again is not new to us because we know that even from our very basic concept of force and momentum, when we say dp by dt is equal to 0, where p is equal to constant, that is momentum is equal to constant. This constant term is there with us. How we are going to imbibe in quantum mechanics, we will be learning in the subsequent slides. Now, principles involved in the constancy in time are called conservation. In conservation laws are not new to us, but how we are going to use them, we will see. Now, this is what our session will be directing upon, is that in quantum mechanics, there is a close relationship between law of conservation of a dynamical observable and the corresponding symmetry operation of the physical system. That means, if there is a dynamical, if there is a conservation of a dynamical observable, let's say momentum, something like that, then what will happen to the symmetry? Which one, then how it is related to symmetry? The constancy of a physical variable implies the Hamiltonian of a physical system is invariant under a certain symmetry. So this line, this we are going to do it again and again in our subsequent slides. Now, just because we are reading symmetries, we are trying to explore symmetries, we need to classify them. Classified generally into geometrical symmetry. Today we will be only learning about geometrical symmetries, these symmetries associated with space and time. We will not be learning dynamical symmetries, which are generally involved in particular features of an interaction such as Coulomb interaction or such interactions, where the symmetry involved is dynamical symmetry. We will be only learning about geometrical symmetries. Now, what about, there is another classification, continuous symmetries associated with displacements, time, space and rotation in space. That is our traditional symmetry, traditional conservation laws which we have been learning, or traditional things like what we have been learning in the beginning, like our momentum, our Hamiltonian, our angular momentum, these things. So they are energy, that is they are continuous symmetry. And new symmetries which we are learning right present, they will be like inversion of space, like parity or time reversal. We will call them as discrete symmetry. And the last and not the least symmetry is our permutations. Now, what do you mean by permutation? Permutation means rearrangement of, that is, if you have arranged the object as 1, 2 and 3, then you can also rearrange them as 3, 2, 1 or 2, 3, 1 respectively. So there, what happens to the identity of the particles? Will we be able to distinguish them? And this part is dealt with permutation symmetry, which we will be discussing in our next session. So let us just make a classification that there are geometrical and dynamical symmetries, there are continuous and discrete symmetries, and there is a permutation symmetry. Now, that is the main headline of our topic, symmetries and conservation. So we know that A by dt is equal to 0. If A commutator, then where do we get this? This is again in quantum mechanics and Heisenberg's equation of motion. If your Heisenberg's equation of motion, again similar expressions can also be found in Ehrenberg's theorem and Duvalier's theorem in classical mechanics also. So what does it say? Observable is a constant in motion if it commutes with Hamilton. That is the basic, that is dA by dt is equal to commutator bracket of AH. So if dA by dt is equal to 0, then AH is. Now in quantum mechanics, whenever there is a transformation, translation or rotation, we associate a unitary vector, the general form of unitary vector, where it is A UA equal to e raised to minus I epsilon. Now let me tell you one thing, that here e raised to exponential, this exponential term is a series, not a single term. If e raised next is e raised 1 plus ix by 1 factorial and so on. Why I am telling you will realize it. Now, when you do this operation, you will get H. It is a unitary operation. Now, from 2 to 3, how did we jump? So that hint is given here. UA of H is equal to HUFA from 1 and 2. So now what is 1? 1 is AH is equal to HA. And what is 2? U is equal to, let us we can write approximate equal to 1 minus IEA. Now substitute UAH. We get the same as HUA. Only thing you have to consider, that is the primary thing which you have to consider, is that you have said this epsilon. Epsilon H and H epsilon should be equal. Then only this condition will. If this condition holds good, that is okay. Now what does this mean? Let me once again repeat. This is okay. Now you are having a UA. You are defining a unitary operator associated with this observable A. Again, this is so once you get this UA equal to UA from 1 and 2, expand 2 and then use UAH. Use AH is equal to HA, and then when you substitute here, so UAH UA dagger will becomes UA UA dagger H, and that is UA dagger is 1 from unitary transformation, so H is equal to H, and it represents a unitary transformation. What does it mean? It means that an observable corresponding to an operator is conserved when Hamiltonian is invariant and observable corresponding to a operator is conserved when Hamiltonian is invariant under unitary transformation generated by it. That means that when there is a conservation law, it implies existence of a symmetry transformation for this. Now, this general thing is going to be used in all other subsequent conservation laws and symmetry. Now, this is a very informal state of Noether's theorem, 𝐸-Noether's theorem. Though 𝐸-Noether's theorem was proved using classical mathematics, but because it was a statement first made by that mathematician, so that scientist, we will remember her, and we will use an informal statement of Noether's theorem. Now, moving to the next topic is symmetry and degeneration. Now, how symmetry and degeneration are related? Let us see. Suppose we have a ket alpha representing an eigenstate of a system, such that H alpha is alpha, that is Xi is equal to Ez. No problem. Now here, suppose you apply a unitary such that HUA alpha here is HUA alpha. We know HUA is equal to UAH, UAH alpha. This becomes UAA alpha. Now, if you look here and here, what is common? Here, E is common. That means when you are having two different eigenstates, that is UA alpha and alpha, you are getting the same energy E. This is a very interesting observation or interesting phenomenon, let us say. Here, if UA, if alpha are linearly independent. Now, linearly independent, one cannot be expressed in terms of another. That's linearly independent. The basic thing. If alpha is linearly independent of UA alpha, this energy that means alpha and UA alpha correspond to different eigenstates with same energy value. And why is it possible? Because HU is same as UH. Then only you are able to get. So therefore, what you will conclude? You will conclude that degeneracy is a consequence of invariance of Hamiltonian under a symmetry. Once again, let us say this alpha and UA alpha are having same energy eigenvalue E, which means that they both are that energy eigenvalue is degenerate. Hence, is a consequence of if this HU and UAH was not there, this would have not been possible. It's a consequence of invariance of Hamiltonian under a symmetry transform. So with this background, we will directly go to the individual symmetries. That are the translation symmetry, rotation, translation in time, Now displacement in space, what does it mean? So say it's conservation of linear. Now let us take 2 points Q and P. Now here wave function at point P, displacement is same as the wave function at Q where P was. So now the wave function here will be same as here when you move it back. That is when you move it by a value delta. So this is also not approximately equal to, because there are a lot of terms. We use 1 minus I delta rho alpha, where alpha is the Hermitian operator. Let me tell you one thing: all physical observables are Hermitian operators in fundamental postulate. So now here UA delta rho, we are not directly writing as e raised to minus I delta rho A. We are writing 1 minus I delta rho A, and we are using the term. So when you operate it, when this unitary operates on psi r, it becomes psi dash r delta rho. This I had explained earlier. So once again, let me tell you, psi of delta rho, UA of delta rho psi r, that is unitary operating on psi r, gives rise to a new waveform, right? So, r minus delta rho. Now, if you substitute UA here, that is 1 minus I delta rho here, and then expand the right hand side, that is psi r minus delta rho, and psi r minus delta rho by Taylor's expansion. I have given you the Taylor's expansion hint here. What is Taylor's expansion? If you write psi s f a s r and h s so and so, then you will get this answer. So finally, this will be 1 minus delta rho psi by dou x. If you take the x direction. So generalizing it, we will write it as, instead of dou psi by dou x, we will write it as. Now this del again is interesting because of a momentum operator. So once again, let us write it down. 1 minus I delta rho dot alpha psi r is P. P is minus I h cross delta. Or generally we remember P as P is equal to h bar by I d by dx, single dimension. So this delta. Now you substitute for delta by P. Then when you compare, look at the left hand side, look into the right. You will see that this term alpha and this P, they connect by a term operator. Earlier we had written as alpha because we didn't know what is correct value. We are only having the idea it's an Hermitian operator. We are first following the basic principles of our quantum mechanics from which we started. Now we have a definite value for this operator, that is UP delta rho is 1 minus I by delta rho P. Now this can be written as, again, to revert back exponential thing, you can use it, and again this way, for convenience we can also write it approximately equal to, because it's a big series. So but we'll take the first two terms. So when you are taking for a finite displacement, remove this delta, you simply write as UP rho exponents I by h bar rho dot P for finite. Now this is the analysis we have done. Once again, let me tell you, substitute u psi r, expand psi r minus rho. So use this Taylor series expression. You will get a delta rho d by dx first term. Second term you will know. So 1 minus delta rho d by dx psi r whole rest. So this term will be taken as delta. We substitute for delta, that is minus ih delta. The value of alpha, substitute alpha, and you get the unitary operator. Now here, some things we need to find out. That is, generator of translations in space is unitary operator. Then let us go back to the slides immediately, because where we had written AH, and then we had proved that UHU is equal to AHU is equal to H. Same logic apply here. Invariance of H. If you want H to be invariant, that is, if you want UPH equal to HUP, then what should happen? That is the first case, Heisenberg's equation, that commutation relation. AH instead of AH, here PH. PH should be equal to 0. That is conservation of linear model. So we will make a statement, because once we have done this analysis, we made a statement. Conservation of linear is the consequence of translational invariance of Hamiltonian. Okay? So again, now this is not enough. We need to check whether this should work, because if you are doing a unitary operator, it should work for Schrodinger equation, the fundamental. Let us check whether this is working. So this is our original equation. Dou psi by dou t is equal to x psi. Now the transformed equation will be psi dash rt is equal to up psi rt, and should obey the same Schrodinger equation. So let us substitute here up h psi. You know up h psi is h up psi. So up psi is psi star. So it has the same form. So here it is ih dou psi by dou psi by dou t h psi, same as ih cross dou psi bar by dou t. Now we are convinced that the condition which we have put correctly is obeying these figures. Now let us discuss displacement of time. Once we have covered translation thing, conservation of linear momentum. Now we will be discussing displacement in time, that is conservation of energy. Conservation of energy. Let us consider translation in time of a wave such that psi r described in the particle. The wave function translated in time will have a new coordinate, t plus tau for psi star corresponding to t in psi, and use the same basic principles which we have used for our momentum case. Make UH tau is equal to psi star t equal to psi t minus tau. Previous thing and the same thing, that condition. Now, expanding the right hand side of equation in Taylor. Expand the right hand side in Taylor series. So you will get an expression like psi r t equal to tau psi by t, and d by dt is equal to minus h by h cos. So finally, we are skipping the steps. Finally, we'll arrive at UH tau equal to exponential I tau Hamiltonian by h. Once again, let me repeat. I think whenever there is a transformation, the basic thing, we are only using the basic thing which we started. Symmetry and conservation law, there was an unknown conservation operator. Here the operators and other unknown. Here there is a transformation. That expression, expands in linear in Taylor series. Again, Taylor series hint is given. So once you get in Taylor series, compare the terms, and finally you get the expression, which tau is equal to exponential tau. Now here two things: invariance of Hamiltonian under translation. Invariance of Hamiltonian under translation requires UH tau is equal to HU. Expand it, substitute it, you will get otherwise. Now, H commutes with H if it is only independent of. You will realize previous term there is no H will commute with UH. It is independent of. Okay. Time independent of H. Time independence of H. Hamiltonian means total energy. So, what does it say? When the energy is not varying with time, then it is conserved. So time independence of H means total energy of the physical system is conserved. I hope you get through this. You derive here, go back, prove this. If it is proven, this is only valid when H commutes with H, and if it is independent of T. When H is independent of T, time independence, or H is time independent, that itself means physical system that has the total energy is conserved. So finally, what the conclusion we will make: total energy of the system is conserved if system is invariant under translation in time. Now let us move forward. Now let us go to another conservation which also we know from the beginning in a different mode: rotation in space. So rotation in space, that is conservation of angular momentum. Now, angular momentum, this graph is very familiar to you because this graph is the one which we use when we study vectors, when we play rotation map. Having a center point O, you are having x and y, slightly tilt the axis anti-clockwise, you get a new coordinate x prime and y prime, and then again do the analysis. X prime is equal to x cos theta plus y sin theta, and y prime is equal to minus x sin theta plus y cos theta, and z prime to z. Now here, this should not be difficult because again this is the basic notation thing which we already know from our vectors and matrices arranging this rotation matrix. We already know. Now here, what we will use is that theta is very small, infinite. Cos theta goes to 1 and sin theta goes. So when theta is very small, cos theta goes to 1 Sin theta goes to theta. Now, when you use the psi prime xyz, psi prime xyz is actually psi prime, psi x prime is x plus y theta. And what is y prime? Y, that is cos theta is 1. Y minus x theta and z is z. So again, this is approximately equal to. Again, apply the Taylor series. This you have to find yourself because it is a 3 variables, multi-variable Taylor series. Find out, and you will get an x. First term is same every case. Second term it will be theta will be common. Y d by dx minus x by d. Are you familiar with this term? That is d by dx. If you say, you can write it as px. So h bar by I d by dx. And this also you can write it as py also. This is the momentum px minus x py. In all these relations, we know this should be LZ. So LZ, as it is L is again R cross LZ. So do the substitution. 1 minus, I have skipped the substitution because I have done it in detail in the momentum part. Please follow the same things. And then is the Taylor expansion. Substitute here. You get LZ from here, and then finally you get the value 1 minus I cos theta Z. This XYZ. General unitary operator, we will slightly modify, will not use, we will use J. The total angular momentum is equal to L plus. So this is the uj and theta. This is rotation minus I dot h. This is the axis and dot j. Theta and dot j is the angular momentum of the system. Here we are not doing anything new. We are only reinforcing what we learned earlier. How to write a rotation matrix. Cos theta, sin theta, minus sin theta, cos theta. That you are getting. Use the Taylor expansion and use the same procedure as we have done for a linear momentum. But the difference is there it is not there it was a simple translation. Here it is a rotation. Operators will vary. What you get? You get is that conservation of angular momentum as a consequence of rotational invariance of the system. We are not again going to UH and HU, we will get the same result. Now, with these 3 parameters, like we have done translations in space, rotation, and time independent of Hamiltonian. These are basically known as continuous symmetry, and they are also known to us in some form or other previously from our previous model. But the next 2 things which we are going to learn are slightly new to us and slightly more complicated because they are dealing with not just quantum mechanics, lot of particle physics and nuclear physics. And those 2 parameters will be called also discrete because they involve in reflection and other things in time. That is space inversion parity and time reversal. Space inversion parity, what do you mean? Suppose you are having a right-handed system. If you are reflecting it in origin, simply just try to visualize. This is a right-handed system. Just to reflect it, what you will get. X will, Y will go this side and with flip that will go down and you will get space inversion. How do you define space? Space inversion is an operation in which axes of the coordinate system are reflected through origin. That is, as I have told you, you are having a set of coordinates x, y, z. Simply reflect it. So what happens? Y goes in the opposite direction, x goes in the opposite direction, z goes in the opposite direction. That is space inversion. Now, this is also if a physical system is invariant under space inversion. This physical system and this, we can say the mirror image, if both are same, then that possesses reflection symmetry. Reflection symmetry means if a physical system is invariant under space inversion, then it possesses reflection system as both systems are mirror reflections of it. Now, how does parity come into picture? As we have mentioned, since there is a parity between the system and its mirror image, there is a connection, there is a match. Parity, there is a, so we will call space inversion is also called parity operation. Operating parity on a system. Now let us check 2-3 systems because you will learn instead of deriving a U, I am directly P for parity. We will discuss it later, or we will come to it later by real parity. Now, parity operator operating on psi. Psi r is a displacement. Displacement, what will happen? Because again it's the vector, it will reflector, it will invert. So psi prime r is actually psi. Is the parity of. Now, P R P dagger. When you do a parity operation, when you say there is a transformation, there is always a minus. Similarly, when you use P and small p is our momentum. There is again a minus. But when you do an operation, parity or symmetry operation or a unitary transformation on L, it does not change. Because L is an axial. What is the concept of axial vector? Obviously, then you have to define what is a vector. R and P are vectors. And vectors transform the same way as the coordinate. Suppose there is an inversion of coordinate, vector is supposed to invert. Whereas axial vectors have something more than that of a simple inversion. There is some other irregular symmetry involved, or they are something different. Generally, they are expressed as cross products. Mathematically, we will. And they don't invert. That means they don't show the property like vectors in this case. That is the basic fundamental property, even though they are called vector. And why we define a vector is transformation. Vector is defined as the quantity which transforms the same way as the coordinates is not followed. Such vectors are called axial vectors. So most of our physical quantities like L or torque or magnetic field, they're all axial vectors. So here parity also affects them. Normal vector parity is affected, axial vector is not. Now, what happens if you reflect a thing twice? You apply p psi, it gets inverted. Again apply p psi, it again gets inverted. That means when you do an inversion twice, the likely result is that is back to its original position. This p square is equal to 1. It went to minus 1, it became again inverted. So p is equal to p. So now we will say parity is Hermitian as well as. Now we have described only the unitary property. You can also prove that parity is Hermitian. Because what is the basic property of Hermitian? You are having an operator A, or if you are saying 𝑥𝐴𝑦 is same as 𝑎𝑥𝑦. Substitute xy instead of A, use P. 𝑥𝑃𝑦 same as Pxy, X and Y. So you will get the same. Now, I had told in the beginning, I am not going for an elaborate unitary operator because parity itself is good enough for Hermitian and unitary. We don't need a separate unitary operator like elaborations of an exponential. Those things we don't need. Simply, we will set UP is equal to P. That's why in the beginning itself, I have used P as a unitary operator for unitary operations itself. I hope you are convinced. We once again tell you, if you apply parity twice, you get 1. P is equal to P inverse. Parity is unitary. So if parity is unitary, what is the need for a new unitary operator? So we will set UP. That is the unitary operator associated with parity transformation. This P itself. Now, wave functions will also be classified on the basis of the operation by the parity function. That is, E is operating on psi r. You are getting plus. It is an even wave function. It is getting minus. It is odd wave function. So again, an operator could also be characterized. Parity doesn't stop there. An operator could also be characterized even and odd depending on the sign of the parity. So parity transformation will decide. So actually there is a classification again. So this parity operator is making operators also classify as odd and even, which we have not seen. That is, when there is a transformation, please look here. PAP dagger. PAP dagger. If you are getting minus, that means it's anti-commutative. AP plus PA is equal to A. If you are getting PAP dagger is equal to A, such that AP is equal to PA. AP is equal to PA because P dagger is inverse. AP is equal to P. Then it is. So, on the basis of this, that is, on the basis of whether a parity operation is changing, you can classify an operator, even classify wave function. In the last line, a physical state has a definite parity if the Hamiltonian is invariant under a parity transformation. So this is a general statement. It's not the ultimate statement because you must be knowing, or you will tend to know in nuclear physics and particle physics, that although in the beginning all interactions are supposed to be having a parity conservation, later on it was realized that weak interactions not follow that. And by Yang propose the paper. But more than proposing the paper, it was Professor Wu who confirmed parity is not considered, violated. There is a breaking of symmetry happening there. There is a parity violation in weak decay. So, though this statement holds good, but that doesn't mean if there is a parity violation that there will be no reaction, not be a forbidden reaction. Weak interactions are happening, and beta decay. Beta decay again is a example of weak interaction. Now, once you are done with parity, we will move forward and we will discuss time reversal invariance. Time reversal invariance is something which is of special importance. Why it is, we will listen, we will understand, try to understand. Time reversal operation, we will simply say time is reversed. Let us say put t and make it minus t. Is it true? How true is it? Let us, we will be checking. Because maybe a classical definition. Quantum mechanically, is time inversal invariance meaning it is just t then minus t? Or is there something more than that? Let us see. Now again we know if observed with such as a position coordinate is time independent and therefore will not change under this operation. Again, this is a known thing because r is not depending on time, why it should change? But a momentum is depending on velocity. If velocity will change, velocity is depending on time. Therefore, momentum, angular momentum is time dependent, and therefore, when time reversal operator is operating, they are likely to change. Now, with these two data in mind, right, when there is a transformation, r t dagger, there is a unitary transformation, you will get r, but t dagger will get minus 2. So now here we will substitute x prime px prime. X prime px prime, when you're subjecting it to a transformation, you will write t x px commutator bracket t dagger. Again, this can also be written as ex t dagger, t ex t dagger is same as this x only, and this is what? This is minus px. So now look at equation 15. In equation, what does it say? Xps is ih. So t ih t dagger equal to minus ih. This is a profound state. This is something which is making this time reversal invariance very different from all other parameters which we have studied, whether it is linear momentum, angular momentum, even parity, which is a discrete. Because why? Let me once again go. T r t dagger is equal to r, t dagger is equal to minus. X prime p prime px prime can be written as t x px t. I hope you agree. This can also be written as, you can take everything inside, x dagger x is equal to x minus x minus. Now this thing, that is when an operator is changing a quantity into its conjugate, then you will call it as an anti-linear operator. Now one thing I must tell you, all the operators which we have studied starting from angular momentum to parity, they are all linear operators. Now, what is the basic concept of an anti-linear operator? Suppose you are having a function, suppose a c x ket. You apply an operator ax, so it becomes a c ket, e x ket. Once you apply it, if you are getting c star x, ax, then what is happening? He is getting converted to system. That is anti-linear. Anti-linear property is making this time inversal reversal invariance different from us. Now, let us continue with our time reversal. Now, once you are applying, again we said, we want to test whether whatever we are saying, we will apply it in our Schrodinger. In the beginning we had said, if you check, if you make t to minus t, is there a time reversal? Or it is just a classical definition which we need to improve? That was my question when we started the PPT. Let's go back because this is what we described. Time reversal is the operation in which t is reversed, t goes to minus. How good is this answer? Let us substitute. Let us take the Schrodinger equation. H bar dou psi by dou t is equal to. Now substitute, instead of t, write minus t. So write minus ih bar dou psi by dou t is equal to hr minus t. Now here, when applying time reversal operator, ih bar dou e psi by dou t equal to h t psi by t. Now you will realize that T psi RT is not same as psi R minus T. The left hand side and right hand side are not matching. The left hand side is not matching. The right hand side is not matching. Look carefully. Left hand side there is a minus sign. And the right hand side there is no sign. So if you are matching right hand side, left hand side and right hand side are not matching. How do you control? But if you take the complex conjugate of 17p, you take the complex conjugate of 17p, so you get IH bar phi star R minus T by D for the mistake. So there should be only one sign. It should be H psi star R psi. This equation is similar. That means you are preserving the form of the Schrödinger's equation. See, this equation is similar. So that means time reversal operator T psi RT is equal to psi reversed RT or psi star. So time reversal is actually a conjugation which we have already discussed. So time reversal is not just blindly we say. Classically we can say, okay, time reversal. What is time reversal? Simply substitute it to minus. Actually, it is not just that. There is something more to it. Once again, let us try to understand time reversal. Our position coordinate doesn't bother about time reversal because it's not dependent. Momentum coordinate bothers because again it's dependent on velocity. Right? Now, whether T2 minus T is a genuine definition or is a correct definition, we will check by substituting in our so-called the standard equation which we assume we should where all the ties should work. Our Schrödinger equation. Right? Substitute here. Put T2 minus T and then use the time operator. We'll realize that they are not matching. If they are not matching, that means we need to make some correction. What is the correction? When you are using a conjugation, you are getting this expression. IH bar rho r by dt is equal to xi star. The same in the same form as this. So when something is in the same form, then you will call it. It's okay because it is preserving the form. So therefore, T psi RT, psi reverse is psi star R minus T or just minus T. Psi star R minus T. This is a profound fine. Now applying time reversal and using it like T IH bar psi by 2. This can be written as T, you know already H side. Then T dagger T because T dagger T is 1 H side. So once you apply, then you compare left and right hand side. IH bar rho r by dt is equal to T H T star psi star RT. It comes out. And when you compare left and right side and you compare both equations, you get H is equal to T. So H is actually a transformation is going on. Hamiltonian is now one thing now because we have discussed time reversal, we have discussed how what type of operator time reversal is. Time reversal how different it is. Time reversal generally is not a unitary because all the operators till now we discussed are unitary operators like our momentum, like our angular momentum or our Hamiltonian of time and all. But this operator not unitary, anti-unitary operator. Again, so therefore T is actually not just a U, but also there is a charge conjugation factor. There is a conjugating factor. Is this. So again, time reversal, like our parity, so it is difficult to check. It is expected that every reaction suppose should be obeying time reversal. It's not always true. There is a breaking of time reversal that in certain cases in nuclear and particle. For the time being, we'll stop it here. Now, we will briefly discuss what all things we try to understand in this module. First is we try to define symmetry. Symmetry is nothing but if an object, if a system remaining unchanged under a certain rotation, reflection, and in general a transformation, we will call it as a symmetry. Then we discuss different types of symmetry. Types of symmetries again they are continuous, there is discrete, there is permutation. We have discussed three continuous symmetries and two discrete. Then we discussed that invariance of Hamiltonian under space translation corresponds to conservation of linear momentum, and total energy is conserved when Hamiltonian is invariant. If Hamiltonian is invariant under time, translations in time, his total energy is conserved. And when pH is equal to 0, which again comes from proving that pH is equal to 𝐻, then the essential condition becomes pH is equal to 0, Hamiltonian is. Finally, we discussed angular momentum as a consequence of rotational invariance of the system. Now, rotational invariance, we discussed about a vector. We discussed that there is a vector, let's say axis xy, rotate it in the anti-clockwise direction to get a term, to get new coordinates x prime and y prime in terms of cos and sin theta. Substitute cos and sin theta, do the analysis, take the Taylor expansion on the right hand side, get an UP exponential IEJ. That's now, then we discussed two symmetries which were comparatively new to us. That is a space inversion, two operations. Space inversion or the parity operation. Parity operation or space inversion operation again is a discrete operation because it's and again it associated with inversion or reflection of it. Again, parity information operation, we don't need a special unitary transformation because parity operator itself is Hermitian unitary. So our need for generating a unitary transformation operator from the Hermitian operator is avoided. Or let us say we are able to directly use PS. And then the last one is the time reversal operator. Time reversal operator is entirely different from all these operations because time reversal operator is antilinear. Antilinear is a serious because when it is antilinear, all the other things are linear. There is a unitary. You can't call a unitary transform. We are presenting T as U and some conjugation. That is the conjugation. Again, time reversal classically means T is equal to minus T, which we are not following. Which we initially we followed and doubted. Then finally we realized not simply going to minus T. It's also a conjugation. Let me go back and try to express it. That is, E psi r T is not simply psi r minus T. We say if it is a reversal, there is a conjugation also associated. Now, so therefore, time reversal is a antilinear property, anti-unitary. And again, because antilinearity property doesn't directly associate with a physical quantity, the physical variable needs some superposition principles not follow. So therefore, we'll never say that time reversal is conserved. So these are the summaries. Thank you.
Thank you so much, ma'am, for this informative session. We would like to have more live sessions with you. I would also like to thank all the participants present here for their active participation and valid questions. And see you again in the next session. Thank you so much.
Thank you, madam. Thank you.